And the next data structure that's typically discussed after linked lists are trees, specifically binary search trees. But before we get into trees, I want to discuss a bit about some of the prerequisite topics that are used inside of trees. You want to get a good handling of these concepts so you're able to understand the concepts of trees without having to stumble over all the prerequisite knowledge. So the first thing that we're going to cover in this video is recursion. And recursion is a very interesting programming concept that actually, it appears in both math and computer science, as well as maybe some other fields. And it's the essentially concept of self-referential functions. So when you have a function inside of Python, you know that typically you would return like a value from that function, or you return nothing from that function. In recursive functions, you're actually going to make a call to this function that you're inside of the function itself. So you're going to have a function calling itself, which is seemingly a bit of a weird concept, but hopefully by the end of this video and by the end of all of the concepts on binary search trees, you'll have a really good understanding of recursion and when it's typically used. For this video, I'm going to give you a very simple example that originates from math. We're going to take a look at what the problem actually is, and we're going to take a look at how we can implement it inside of Python. So the problem I'm going to be taking a look at is the Fibonacci sequence. The Fibonacci sequence is a special sequence of numbers that follows the following rule. The function's value at 0 is equal to 0. The function's value at 1 is equal to 1. And generically, the function's value at some number n is equal to the function's value at the thing before n plus the function's value 2 points before n. So let me give you an example. If we want to take a look at f at 2, for instance, f at 2 would be equal to the function's value at 2 minus 1 plus the function's value at 2 minus 2. This in turn would be equal to f at 1 plus f at 0, which as we defined here, f at 1 is equal to 1 and f at 0 is equal to 0. So that gives us a value of 1. And then you'll see that f at 3 will follow a similar concept. It will be f at 2 plus f at 1, which in turn would be equal to 1 plus 1, which is equal to 2, right? And that pattern will continue on and on and on. What you'll notice here is that this function is self-referential, right? We reference the previous iteration of the function, as well as the second previous iteration of the function. This is referred to as a recursive function in the same way in mathematics as it is in computer science. You'll see a lot of parallels with them as you continue to study computer science and in turn continue to study math. You'll begin to see more and more how math is linked to computer science and how computer science is really just applied math. So understanding this, let's take a look at how we can implement this inside of Python. It's fairly interesting to see how that works. So let's take a look at it. I'm going to start off by defining the factorial function. So we'll call it def factorial. And the factorial function will take in a value n. And what we're going to do is we're just going to walk through each of the pieces of the function. So for instance, if n is equal to 0, right, then the function's value is going to be 0, right? If the function, or n is equal to 1, the function's value is going to be equal to 1, right? And then in all other cases, the function's value is going to be equal to the value of the function at n minus 1 plus the value of the function at n minus 2, right? So those are the three cases that we discussed there. Now, walking through this sort of factorial function and how this sort of logic works, you just have to think about essentially what that function was doing when I was describing it in mathematical terms, right? So picture that you put 3 into this function, right? What would happen is it would check, so does n equal 1 or 0 or 1, right? It doesn't. So then it will come to this call here. So then it will call the factorial with 3 minus 1, which would be equal to 2. So we would get a call to factorial at 2, and we would also get a call to factorial at 1. Factorial at 2 is going to take a look at these two conditions again. And since it's not equal to 0 or 1, it's going to take a look at this function call again. So from this, we would end up with another call to factorial at 1, as well as factorial at 0, right? So maybe just to clarify this a little bit, the first call was this, right? This was our first call. And then the second call looks like this right now, right? We call these two functions from factorial at 2, and then remember we were still calling factorial at 1, so we still have that piece, right? All I did here was I simplified factorial at 2 to be its equivalent function calls, right? So when we call this function with n equals 2, we get a call to factorial at 1 and a call to factorial at 0, and then we still have this factorial at 1 that needs to be resolved, right? So this is what we have so far. We can think of this like an equation, right? So we continue on and we see that factorial at 1, right, is equal to 1. And then we see that factorial at 0, n equals 0, would give us 0, right? And then factorial at 1 would give us 1. And you can see that it gives us an answer of 2, which is what we expected, right? So really, that's the way that you should be thinking of recursion. Always break it down into pieces like that. So let's just do another example here quickly. Say that we were doing the factorial of 2, right? On the first iteration, we end up with factorial of n minus 1. So that'd be factorial at 1 plus n minus 2, which is factorial at 0. When this calls with 1, we end up with 1. And when we call with 0, we end up with 0, which gives us a result of 1. So you can see how we can continually simplify. It'd be the same sort of thing if you do 4. If you do 4, it would be 3 plus 2. And then you would end up with, 2 plus 1 and, the same sort of thing, right? You would just sort of expand it out from there, right? You would have 2 plus 1 and 1 plus 0, and then you would have, 1 plus 0 plus 1 plus 1 plus 0. And the idea is that you eventually end up at terms that return actual values rather than returning recursive calls, right? We continually break down until we end up at values that don't call the function back again. So there's a few things to keep in mind here. The first is that recursion always has to have a point where we return a value rather than returning a function call. When we return a function call, we make that recursive call. However, the recursive calls need to end at some point. So at some point, we need to end up at something that isn't a function call. This is typically referred to, I believe, as our initial condition. And it really helps to sort of write out like how the function is going to play out in a similar way that we wrote out the actual factorial, or not the factorial, the Fibonacci sequence, right? Just to note as well, since I mentioned factorial is another example of a recursive function, right? Because you take the value that's provided and you multiply it by, minus 1 of it, and then minus 2 of it, and then minus 3 of it. So it works really nicely as a recursive function. So this is really all the logic that you need to implement for it. Let's just take a look at a few examples of it just to see how this works. So again, if I print like factorial at 3, for instance, you'll see I end up with 2. If I do it at 4, then we end up with 3, right? And we can keep on picking larger and larger numbers and we'll get different answers each time, right? And you can try out the math and see that it actually does give us the proper answers for the factorial. So what I recommend with this is try typing in like a value and try writing out the simplified function calls. Like for instance, take factorial at 4 and try simplifying that down into the function calls until you get to 1s and 0s, and then add up the values and then try running the program and see if you got the right answer. That will be a really good way to get an understanding of recursion, aside from trying other practice problems. So this should give you a good fundamental understanding of recursion, and as we continue to apply it, you'll continue to understand better what's happening with recursion. And by the end of trees, you'll be a master at recursion because you'll use it so much, you'll be able to do it almost intuitively. So hopefully this gives you a good baseline for it, and from here we'll be able to build up our actual tree data structures using recursion.